discussing charge carriers and how do we calculate exact number of how many charge carriers are there. And why it is important? It's important because that helps us find the current through those devices. So, and when you talk about the current, that's the ultimate goal, right, as a device. But then there is a temperature dependence on how many carriers are there, because if the carriers go up and down, your current will go up and down. So this plot, which we briefly touched on last time, was talking about the exponential temperature dependence of the charge carriers. So in this case, it's talking about electron charge. Sorry, the electron as charge carrier. So same is the case for holes. So in this one, we are looking at the concentration of electrons with respect to 1000 times T temperature, 1000 times. So 1 over T times 1000, just to get a scale in together. So what we see here is there is in a dope semiconductor, there is, for in this case, a silicon dope at the concentration of 10 to the power 15 centimeter per centimeter cube. At low temperature, which means that on the right-hand side, we have negligible intrinsic electron-hole pairs in the system. So electron-hole pair is where the electron jumps, go to the conduction band, leaves behind a hole. So we call it electron-hole pair. And the donor electrons are bound to the donor atom. So even if you have the impurities, so donor electrons are tightly bound to their respective atoms. And as the temperature is raised, these electrons are donated to the conduction band, and at about 100 Kelvin, we see all the donor atoms are now ionized. So temperature, this is what we call ionization range, ionization region. So once all the donors are ionized, the conduction band concentration is now 10 to the power 15, which is the original doping in the system, in that semiconductor. Now, in this case, we keep on ramping up the temperature, and the amount of electron is now constant because all the electrons are in conduction band. We keep on ramping up the temperature until we get to the concentration of the intrinsic carriers, and they become too high. So electron hole pair formation, which is happening because of temperature in the intrinsic semiconductor, that reaches 10 to the power 15. So now if you crank it up further, the intrinsic charge carriers will become more. So hence you get into the left side region. Now, what's the problem with this system? The problem is that if you have a device, the conductivity will change with temperature, and we don't want that. You don't want a computer that operates at room temperature, and if you're traveling to Minnesota and your computer doesn't operate, right? So we need to have same number of charge carriers, whatever the temperature is. So hence, another thing, the most important thing is that we need to dope it high enough that intrinsic charge carrier never become more than the doped semiconductor. So 10 to the 15, this plot is, if you know 10 to the power 10 is the intrinsic charge carrier concentration for silicon. 1.5 times 10 to the 10. So we just take it 10 to the 10 that we are discussing. So we thus dope the material so the intrinsic range extends beyond the highest operating temperature where we will be using that. And this directly leads into the topic today, which is the carrier transport. Whenever charge carriers move, we call it current. So we're interested in how current flows through semiconductor devices. Now, when we talk about current, you know, the basic fundamental definition of current, it's the number of charge carriers passing through a square unit area in a second, right? We all know that. And that happens when we have applied a field. So we'll look at the situations in semiconductor materials. First, we start with no field. So if there is no field, the carrier concentrations, just because of temperature or because of doping, they're just moving out. So they just have random motion. And yes, one electron would move. There's very low probability that it's going to come back to where it started from. But what we can say about those 10 to the power 15 gazillions of electrons, that overall moment of charge is zero. So they are going to stay, the thermal motion is going to keep them in motion, and they're gonna change direction because of scattering, with atoms scattering with each other. But there's no overall transfer of charge, which means there's no current. So how does the current start? Same old, but that's not the full story. But we start with applying electric field. So when we apply an electric field, in this case, in x direction, in plus x direction, each electron experiences a net force which is minus q times the electric field, which is the opposite direction from the field. And this force, it may be not enough to alter the random motion of every charge carrier, but what it can do is it can have an overall effect when you average over all the electrons. We can see there's a net motion of the whole group of electrons in minus x direction. So we are talking about electrons here. If we are talking about holes, the movement would be in the direction of the electric field. Now, this is something some of you may get confused, because when we talk about circuits, we are taking the flow of current in a certain direction, and we take the field and current in the same direction. But here, and it may seem different, but it is not. Electric field, the direction of electric field, whatever we take, the movement of electron will be opposite to that, and the movement of holes will be in the direction of the electric field. Now, when I said it's not the complete picture, so there's always two types of current in semiconductor devices. One is the current which is because of electric field, like we are showing here. There is another current which is called diffusion. Now, when we are talking about a conductor, a metal, the electrons are homogeneously distributed in the whole device. But when we are talking about semiconductor devices, there may be some regions where we can increase the amount of charge carriers. We can shine a light and create many more electron hole pairs, which mean in that region, the concentration of electrons or holes will dramatically increase with respect to the other parts. And that causes what we call diffusion current. So there are two types of currents. I'm just throwing equations at you without going too much into detail, but we'll talk about these equations. So there are two parts to total current in a semiconductor device, and they're called drift and diffusion. So drift is the carrier concentration because of some force, right? So in this case, electric field. And the diffusion is the movement of carriers. What we call diffusion in general terms, diffusion is when things travel because of the gradient in their concentration. The example is the opening of a bottle of cologne. So if I'm standing in a corner and I open a bottle of a cologne, sooner or later you're gonna start smelling that the molecules of that cologne in the other corner of the room, right? So how those vapors are gonna start traveling from the higher concentration to the lower concentration area. This is generally what we call diffusion. Now, there are a few things in this equation. So the overall total current is divided into two parts. One is the drift current and the other is diffusion current. So Q is what we know. Q is the charge on an electron. N is the number of electrons. So now this equation is total electron current. So we would have a similar way of writing total hole current. So we'll just right now just stick to electron current, and then we'll talk about total current in terms of electron and hole current as well. Yeah, so this should be total electron current where it says total current. Now, mu n, there's this thing U with a long leg, we call it mu, Greek letter. Mu n is a new entity which we haven't seen before. We'll come to that. So E is just the electric field. Again, in the diffusion part, Q is the, again, charge. Dn here is the diffusivity coefficient. So it's a constant for many things. And dn of x over dx is just a differential equation, which gives us the difference between the concentration of electrons in x direction, one direction versus other direction, whichever direction we are moving. So we are moving in x direction. Now, mu here is called mobility. Mobility is a special thing only for semiconductor materials, which gives us an idea of the ease with which an electron can move in the material. So it's an important quantity in characterizing semiconductor materials and device design. We don't encounter mobility when we talk about good conductors, metals or copper, because there's no idea of ease or less of ease. They would just flow. But in semiconductor materials, because it's a crystalline structure, electrons will encounter atoms when they're passing. Electrons will encounter each other when they're passing. The atoms which are stationary in that crystalline structure would be vibrating in their own space. So temperature will have an effect on diffusion and drift. So that gets into this component called mobility. Now, mobility plays a big role. We'll talk about that soon. So this is now total electron current. Let me just write down this. This is total electron current. So because same is the way when we will calculate, I'll write E here, just to show that this is the electron current. Now, similar would be way when we would find total hole current. And that would then, when we'll get the hole current, you know, they'll be going in opposite directions, right? So depending on N type or P type, then one type of current would be dominant, and that current would be what would be causing the flow of carriers, electrons or holes. All right, so let me remove this and get on to the next slide. So if you focus on just the drift part, so this mu or the mobility is defined in terms of the average velocity of charge carries in a direction divided by field. That's a very simple relationship. There's a derivation that's behind it, but we'll just stick to this relationship, which is, and we can play around. If we given mobility and field, we can find out average velocity, right? So Vx and these braces around Vx are just to show there's an average quantity that's shown there. And Ex is the same way, it's the field. Now, the current, as we know, is charged. In this equation, charge times number of electrons, number times area times velocity. That's which is gathered into mobility, and we get this equation. Different, slightly different from the equation of current that we know, but it's still the same thing. It's just that we have put the average velocity of a charge carrier into the system, and that there's a reason, and the reason is that the velocity is not a linear function of voltage. So unlike conductors where we keep on cranking the voltage and Ohm's law is valid across the whole voltage region, here there's slightly different thing, and we'll talk about that. That's the reason we have the concept of the average velocity in there. So when there is an electric field, that would cause a drift, and electron or holes, whatever the situation, and there will be an average velocity coming out of all of the electrons or the holes in that system. We bring it all together into equation, which is drift equation only for, drift equation for both electron and holes. So we had first we saw only total electron current. Now we are looking at total drift current. So don't get confused. It's just that the two components of drift and diffusion would make up one type of carrier current. And then if we were to look at one type of current, then we have to incorporate both electrons and holes. So here what we are doing is we are using the mu n and mu p. Now, mobility for electrons and mobility for holes, for a whole bunch of materials are known, and for a whole bunch of semiconductor materials are known, and we plug in those values as it is. There is a, I think in one of the appendix, there's mobility values are given, but we'll restrict ourselves to mobility values of silicon and gallium arsenide, those 3-4 of the semiconductors that we have talked so much so far. Now, there was one thing here, which was Mn star on the right-hand side. So where mu n is equal to Qt bar over Mn star. That's another way of looking at mobility. So those both relationships are valid. In this case, what we are talking about is we're talking about mobility in terms of the mean free time that one electron strikes. Like in this case, we are talking about Brownian motion. How long does it take for it to strike with the next one? Divided by the mass of the effective mass of the electron. This, we have encountered effective mass before also when we are talking about the density of states. This is slightly different than that, but the idea is same, that it is not the actual mass that we encounter when we talk about mass of electron or mass of holes. It's because of the field on the charge carriers, we use effective mass, and we know the values of effective mass also for both cases, for electrons and for holes. So we use that in this relationship. All right, so we'll stick to this relationship for the most part about mobility. We will not get into that Qt bar over Mn star. But this relationship is much more important, because here what we have is we are given in many of the problems, we would be given on, we would be applying the voltage. So we will know the field, and the difference between voltage and field, we'll look at that very soon. So voltage divided by the length is the field. That's how we calculate that. All right, so now when you are taking a small piece of semiconductor, or you think about a small piece of a conductor, we use Ohm's law there, right? And Ohm's law, with V equals IR, we make a plot, we say it's a straight line. So R there is the slope. We get R from the slope of current versus voltage versus current. So, but when we talk about semiconductor devices, the R is slightly different. And the R is, if I lay out a semiconductor material with the width W, thickness T, length L, and I have electric field in one direction, and that would define my electron and hole motion. We can calculate resistance from relationship rho L over area. Area is W times T, which is given here. Now, what is rho? Rho is called resistivity. It is reciprocal of conductivity. Conductivity is, so we write resistivity like rho, and conductivity is, what is it, sigma? Or what is it called? Yeah, it's sigma, right? So this guy is conductivity. Let me type it. And rho is resistivity. So in terms of these two values, which we know again for a material of certain doping, we can find the resistance of a material. All right, so now the resistance of semiconductor material is not straightforward like it would be for a conductor material. And the reason is semiconductor bar contains both types of carriers, holes and electrons. So the resistance is then calculated from this relationship. Now, the physical mechanism of the drift requires that holes in the bar move as a group in one direction of the field and the electrons move in the opposite direction. In both components, when we think about the conventional current, it's different than that, because in that case, it's the positive direction is the flow of electrons, but here the positive direction is the flow of holes and the opposite direction is the flow of current. Now, when we visualize the current carried out in the external circuit by electrons, there is no problem in visualizing electrons flowing into the bar at one end and out at the other, right? So we can then know that it's always opposite to the current. Thus, for every electron that's leaving the left side at x is equal to 0, there is one corresponding electron that's entering at x is equal to L. So the total number of concentration in the bar remains constant. So the overall resistance would be dependent on resistivity and or conductivity. And conductivity is a function of the number of charge carriers. All right, so let's take a look at some basic things that for when we go from then current of from electron current to hole current, we just change to from N to P in those relationships. Instead of using minus Q, that's for electrons, we use plus Q, and that then changes the direction of the current. We change mu N to mu P. And in that case now, just like we had mu N was equal to average velocity minus average velocity over the field. Now in this case, it would be plus average velocity divided by field when we are calculating mobility of holes. So as I said earlier, this is the important relationship when we talk about mobility, which is for holes, it would be plus average velocity divided by field, and for electrons, it would be minus average velocity divided by field. And we know the mobility, we have the charts of mobilities. We know mobilities for a lot of semiconductor materials. We are the ones who apply the voltage, and we know the length of the semiconductor material. So voltage and length, we can find the field. So with this relationship, we can find the average velocity of charge carriers. So, and that leads to another thing where we can then find out current in the system. So here, now, we talked about conductivity on the previous slide. So this is how we find conductivity. So conductivity, if we just talk about electrons or holes, conductivity because of electron would be this. Conductivity because of holes would be QP mu P. So, but this is now the conductivity, overall conductivity. So this sigma is calculated by Qn mu n, which is then plugged into what we had here to find the resistance of the system. Make sense? So if I were to complete this slide, I would write it like this. Q, depending N, would be for N, and P would be for P. So overall conductivity would be found with this. And this is what will give us the result. So you can see that for semiconductor, resistance has a dependence on the number of charge carriers and the mobility. And then mobility has a dependence on a bunch of things. So we'll look at those parts. Now, there are, when an charge carrier, let's suppose electron, when an electron is traveling through a semiconductor material, it encounters two types of strikes. It encounters two kind of scattering mechanisms, if you can call them. Now, those bouncing offs or that striking or the what you call scattering mechanism, they would result into the mobility to reduce. Now, because of that, the overall direction is now being not influenced not just by the voltage that's applied, but also because of the scattering events. So there are two types of scattering events, which is shown. One is impurity scattering, other is lattice scattering. So lattice is the semiconductor structure, right? Where all things are, all atoms are in place wherever they are. And we call it lattice scattering. So when a carrier is moving through a crystal, because of the vibration of the lattice, it would bump into that. So vibration is because of temperature. Now, frequency of these scattering events increases as the temperature increases because the thermal agitation of the lattice becomes stronger, greater. So we should expect the mobility to decrease as the sample is heated, right? So now again, you can see temperature is given at the log scale. Now, on the other hand, scattering from crystal defects, such as ionized impurities. So we talked about electrons and holes, which are electrons are jumping, so ionization happens. So that would result into, again, a scattering event, and this becomes dominant at low temperatures. Now, atoms of the cooler lattice are less agitated, like lattice scattering is less important, but the thermal motion of the carriers, they fighting each other becomes more dominant. So the thermal motion then results into the slowdown of the carrier. So now mobility is not something, just like we thought about conductors, we crank up the voltage and the charge carriers will start moving faster. So mobility is what changes the charge transport through semiconductors, makes it different. And this is showing just the dominant on temperature. Now, so another thing, now, when we talk about a system, mobility will always have to take the smaller mobility. So if there are mobilities because of impurity scattering and lattice scattering, both, the one that has lower value is the one that we'll have to use, because that will be then dominant. So if you think about it, this is like capacitors. So if we add capacitors, 1 over C equal 1 over C1 plus 1 over C2 and so on. So mobility has to be treated now in the same way, because the lowest one is the dominant. So hence, if you have a bunch of mobilities, we'll be using then 1 over mu equals 1 over mu1 plus 1 over mu2 plus 1 over whatever comes after that. Because the lowest one is the dominant one. So we would not then take the bigger number to be dominant. So this is then how we would take the lowest mobility. Now, another dependence that mobility has is on the impurity concentration. So if you think about it, that we can keep on doping and it should keep on becoming better and better conductor, but that's not the case, because now what's happening is the collisions increase. So what we say here, impurity scattering, if you dope it too high, impurity scattering becomes dominant. So what does that mean? That means is, yeah, for a semiconductor to have higher conductivity, increasing doping concentration is not the solution. So we have to then stay within certain region or certain limitations. Because as the concentration increases, the effect of impurity scattering becomes much more dominant, and especially at high temperatures. So here we have a bunch of things for silicon, germanium, gallium arsenide. So the right-hand pictures are just, I've blown up the left-hand ones just to show you silicon and gallium arsenide. So what we are seeing is that, for example, for silicon, at 300 degree Kelvin, mobility is, so for, we know that intrinsic is 10 to the power 10, right? So we'll start from 10 to the power 10, but as we keep on increasing at very higher concentration, we start going down again. So mobility keeps on going down. For silicon, we know that as I was saying, there is stable, given we know mobilities at different temperatures. So intrinsic silicon is at 300 Kelvin is 1350 centimeters square per volt second. And the presence of now this 10 to the power 17 ionized donors, for example, would result a significant impurity scattering, going from intrinsic to this 7 orders more. So hence what we would see is, we would see that at this point, the mobility starts going down. So hence we would reach the same value at a very high mobility that we would have for an intrinsic semiconductor. So just adding more and more does not really help us in achieving more mobility, more conductivity from a semiconductor material. All right, so that's the lower one, germanium. So what you can see here, another thing is the mobility, because of electron at a given temperature, is higher than mobility of holes. And that has to do with the mass. So holes have higher mass and electrons have lower mass. So now you think about a tennis ball versus a soccer ball. So the one which is bigger, it's gonna have more issues in moving through versus a smaller one, right? So electron is a smaller one. So for any given impurity concentration for electrons, you have much more mobility than the same concentration of holes. So that's another thing we can see here, that cranking up for higher mobility for a given concentration, we are better off with N-type materials than P-type materials, right? Again, there are many other considerations that come in when, as a device designer, that whether we have to use a P-type or N-type material there. All right, so another dependence. So now this is an interesting thing where we are talking about mobility dependence, or mobility equals average velocity divided by electric field. Now, here's the thing, that we can keep on increasing the field, but we will not be able to keep on increasing the average velocity. Going back to the mobility consideration, which we just thought. So another way of looking at it is why we break apart from Ohm's law here. What we considered earlier in carrier drift process, that at very high field, our average velocity would saturate. We will hit a plateau. So in this case, what we are seeing is that the what you call the drift velocity, VD, for silicon is shown to level off at 10 raised to power 7. So which what we call as the threshold or VD-SAT, saturation drift velocity. So another aspect of it is that we can keep on increasing the voltage. It does not mean that we're going to keep on increasing the velocity of the charge carriers because of the mobility considerations which we just saw. So what does that mean? It means that if you are given a question where you have, for silicon, for example, here, where you are given the electric field that's there or voltage and the length of the material, and you plug into that mobility equals average velocity divided by field relationship, which minus for electrons and plus for holes. And we find out the average velocity. If that is hitting, that's more than VD-SAT, we would then take the VD-SAT value. We will not take the higher value when we are dealing with those relationships. So what does that mean? Let's take a look at an example. So this is a question from the book where we are given the length of silicon. Let me delete the annotation. What we are given is we are given the length of silicon material, we are giving the cross section of the material, we are given the doping. And we are given the resistance also, which we could have calculated anyway from that relationship rho L over area, right? So, but anyway, the saturation velocity is given. It's supposed to be 10 raised to the power 7. We just saw that on the previous plot. Or for fields over above 10 to the 5 volt per centimeter. So we saw that also that for silicon field above 10 to the 5 results into saturation in the velocity VD-SAT. So I'm using the word VD-SAT, but in devices, in electronics, we use VD-SAT for something else. But that happens because of this as well. All right. So it says calculate the electron drift velocity if you apply a voltage of 100 volt across the piece. Now we are given the length and we are given the voltage that's supposed to be applied. So we just find the field from here where we just divide the voltage with the length, we get the field of 50 volt per centimeter. And then we say, okay, we apply this relationship of mobility with field where we can find out the VD, the drift velocity, right? So because of the field, how much fast they're going. So we find out for the case of 10 raised to the power 6 volt, it is above the saturation voltage. So hence what we would use if we use 10 raised to the power 7, we don't have to calculate. But now there is this relationship which is for current, I is equal to AQ and VSAT. So from this relationship, we find VSAT and we plug in into this relationship and we get our current. So what we are doing here is we, instead of calculating Q, mu, and N, we are plugging in those values as is into this relationship, and we are using Ohm's law to find the current. So V over R is what we are using here, and that gives us the current from these fundamental values that are given. So now, just to touch upon the other part of diffusion. So the other part which happens is diffusion, which happens because of the difference in the concentration. And it's slightly straightforward because here what we have is we have charge concentration, we have diffusion coefficient, and we have the length of the bar of a semiconductor, and we have the concentration on one part and the other part. So what we will do is we'll just take the concentration on one side minus the other side divided by the length, and that should give us dnx over dx for this relationship. There's one thing that if we are not given the DN, they are always what we call, they are always related by what we call Einstein relationship. It's something easy to remember. D over mu equals KT over Q. D over mu equals KT over Q. So diffusion coefficient or diffusion constant for n-type material divided by mobility of that n-type material is always going to be a constant. And KT over Q, we know that's 26 millivolt to 0.026 millivolt. So we would always use this relationship to find, if one is given, we can find the other one from this. And that value can directly be plugged in into this guy. All right, so that's for charge transport, for in the basics of charge transport in semiconductor materials.